Okay, so I want to spend a few minutes talking about interference from two different sound sources of sound. But to begin with, let's listen to one single source. This is an applet that I downloaded from FET right here from colorado.edu. You can look it up for yourself if you'd like. If we're the listener here, notice as we move closer, it gets louder. Farther away, it gets quieter, as we would expect. If we can change the frequency, well, once the waves get to our ear, we should hear a higher frequency, a little bit louder, lower frequency, a little lower, and very low. Ooh, that's fun. Okay, so that's fine. But now let's see what happens if we're listening to two different sources of sound. Here's my little guy. Let's put his ear right in between the two. And I can listen to the note created by two identical speakers. What we notice is right here, we see crests and troughs, the dark and light spots, regions. When they overlap, two dark spots create extra dark. That's constructive interference. Likewise, two troughs lining up create extra trough, right? Extra deep trough. Those are all regions of constructive interference. Now, so along this line in the middle, we have a region of constructive interference. Let's listen to what that sounds like. Right there, right in between. Now, if we notice, if I'm just off of that region, I have this sort of grayed out region where a crest from one is lining up with a trough from another, and those are essentially canceling each other out. So let's see what happens if I put my ear there. It gets very quiet. And we have these alternating patterns of loud and soft points where the waves are alternatingly, constructively, and destructively interfering. Okay, so let's see what this looks like. All right, I'm going to try to draw this where I have two speakers. Oops, let's get a pen. I have one speaker here. Here's speaker one. And I have speaker two somewhere else down here maybe. And I have my ear kind of somewhere in between, but not equidistant between the two of them. Does that look like an ear? Let's put an earring here. Maybe make a face. Oh, this is an ugly fellow. Hi. He's got teeth. Oh, Homer Simpson hair. Oh man, he's ugly. He needs a nose. There you go. Maybe some eyebrows. Oh yeah, now he looks human-ish. Anyway, so I have a speaker at speaker one. It's creating a wavelength. It's creating, let's make it orange. Orange, you're glad I didn't say banana? Oh my God. Okay, so here's the wave that comes from speaker one. The wave coming from speaker two, I'm going to try to draw it exactly the same. Looks something like that. And let's see how many wavelengths it took, right, to get from speaker two to the ear. So that distance here, well, it's about 2 wavelengths exactly. Whereas here, we have 1 full wavelength plus a half. So that's about 1.5 wavelengths. So what is it going to sound like when it reaches my ear? Well, if we notice, the 2 waves that are getting to my ear, one is a crest and the other is a trough, which means we're going to have destructive interference. And the reason we have destructive interference here is because the distance that speaker 2 had to travel relative to speaker 1 is exactly half of a wavelength off. So this one had to travel 2 full wavelengths to get to my ear. Speaker 1 sound only had to travel 1.5 wavelengths. So as it turns out, what we care about, and let's make sure you can see the colors okay, is we care about what's called the path length difference. Path length difference. Delta D, where delta D is the difference, I don't care whether it's positive or negative, of D2 minus D1, where I'm going to define now this distance here as d2 and this distance here as d1. Okay, so if our path length difference delta d is exactly equal to some whole number of wavelengths where m is equal to 0 or 1 or 2 or 3 or so on and so forth, then I have constructive interference. Constructive interference, right? Not the case in this picture. Interference. If delta D is equal to a whole number of wavelengths plus exactly a half of wavelengths, where m is again 0 or 1 or 2 or 3 or so on, then we find we have destructive interference. So let's see. So here we have, these are the figures from your book, which I think are fairly well done if you look closely at what they're talking about, right? Speaker 1 is emitting these yellow waves and speaker 2 is emitting these red waves. The path length difference, this delta D, is exactly one wavelength. And you can see then the waves are always lining up with each other, crest to crest, trough to trough, and we get only constructive interference. So this is our condition for constructive interference. The destructive interference occurs when the difference in path length, right? Here's where I'm listening, the dot here, is some half number of wavelengths. And it could be, full wave shifted from this, but the base is that I'm half a wavelength off. And we see that whenever we have a crest from speaker 1, we have a trough from speaker 2 and vice versa. So we always get destructive interference. And so here is our condition for destructive interference. Now, you can go ahead and try your clicker question, the quick check. I'm happy to post answers to these on Moodle if there are any questions. I would encourage someone to start a discussion perhaps about this chapter or about particular problems, and I'll continue to monitor it all afternoon, as well as tomorrow during the day, and basically anytime the children are sleeping during the weekend, and we'll try to understand this chapter as best we can before we get back together on Tuesday. All right, and I'll come back and do a couple more example problems for you, okay?